Welcome to another episode of the 10-Minute Network Workout by J. Cooper Smith. Today we are going to start speaking the language of the computers. I hope you guys are ready because you now have the foundations from the things that we learned in the previous videos to actually really start to appreciate the binary numbering system. Here is our infamous chart. And one of the amazing things about this is a base 2 system. Now I know that you guys are familiar with the base 10 system when we have our 10 fingers in order to find out what the highest number of a base system is. So for base 10 you take 1 less than 10 and 9 is the highest number. So of course we're going to apply the same rule. If we are doing a base 2 operating system, then we're going to take 1 minus 2, and the highest number is going to be a 1. So here we are, with 0 being the lowest value that we can have in our base system, and then if we were to add 1 to that, boom, we have a 1. That is the highest number we have in binary, or the highest number we have in base 2. So like we know from previous videos, is if we're going to add 1 to this, we now convert it down to the lowest value and carry it over to the next column and increase that number by 1. Now we can always lead these zeros without actually changing the number. For instance, if I'm getting paid $10 an hour, right? And my company says, oh, we're going to give you more zeros to the left of your paycheck. Does it really change what I'm doing? It sounds great. Oh yeah, we're giving you more zeros. What I really want them to do is start adding zeros to the right, and that does change what I make. I wish I'd made that much, but no, that's not going to happen. Anyways, so we can always add zeros to the left without changing the numbers, but we can't add zeros to the right. Okay. Now some of you say, well, what about the decimal point? Well, we're not in decimal points. Right now we're just in ones and zeros. Okay, so here we have a binary number of 1, 0. Okay, and we notice that it is in the 2's column. So this is a binary representation of the number that we know as 2. And if we add 1 to this number, right, we're going to increase it and increase it. We'll see that it's 2 plus 1, which is 3, and that's 2 plus 1 is 3, so this is the binary representation of 3. Now if we were to add 1 to this, right, we can't increase this one, so we're going to start at the lowest value that it has, carry over, we're going to increase this 1 by 1, but we can't have a 2 in this system, so it's going to have to be dropped to 0, and then we're going to add this one to 1. So again, all of these could actually be leading zeros up until we get to this point. And so now we're at a number, whoops, it doesn't go there, it goes here. Sorry about that. So this will be a leading 0 as well. So now you can see that this is a binary representation of the number that we call 4, which is 3 plus 1. You can take any binary number and be able to convert it to a decimal number the same way that we always have, even in our decimal numbers. So let's say we take a number out of this guy. I usually would call for someone to volunteer a number, but let's just say 1010. Okay, we're going to take this number, and since this is the 2 to the 0 or the 1 column, we're going to take 0 times 2 to the 0, or it's going to be 0 times 1, which is going to be 0. Again, this column, being that it's our 2's column, 0 times 2 to the 1, I'm sorry, it's not a 0. Oops, get rid of that. It's actually a 1. 1 times 2 to the 1, which will equal 1 times 2, which will equal 2. And then we're going to bring this one over, and this is 0 times 2 to the 2nd power, which equals 0 times 4, which equals 0. And then this number will come down, and it will be 1 times 2 to the 3rd, which equals 1 times 8, which equals 8. We add those up, and we get the number 10. So this number is the binary representation of 10. Now, we can always do our mathematical operations in binary. So if we were going to add numbers together, all right, let's take a number that we're familiar with now, all right, 1010, and let's go ahead and add it to 101 and see what we happen to get. So this is a little plus sign. Okay, so this is addition. So we're going to take 0 plus a 1, which will give us a 1 plus a 0, which will give us a 1, a 0 plus a 1 will give us a 1, and of course we have the leading 0 here, so a 1 plus a 0 will equal 1. Now from the previous screen, we know that this number equals 10, but what was this number? 101 converted over to decimal will be 1 times 1, which will equal 1. Take this, and it will be 0 times 2, which will equal 0, and this, which is 1 times 4, which equals 4. So then add them all up, this will be 5. So the decimal equivalent, this is base 2, and this is base 10. And we know that if we take 10 plus 5 in base 10, we're going to get 15. So if we want to check our answer, we're going to have to take 1, 1, 1, 1. Okay. Remember, this is the 1's column, this is the 2's column, this is the 4's column, this is the 8 column. And again, we're going to take 1 times 1, and then we're going to take 1 times 2. We're also going to take 1 times 4. And then we're going to take 1 times 8. And then if we add all these up, we will get 15. So as you can see, the binary way we add things is very, very equivalent to the same way that we add in decimal. All right, and if we do our checks, even if we convert it over to a system that we know, do our checks, and then convert back like we did here, we can see that our math is still correct. If we didn't happen to know off the top of our heads that 1010 plus 101 is 1111. Okay, this is the language of the computers, and this is our human understanding of decimal. So we're constantly going to be converting back and forth to do our checks until we become more familiar with manipulating binary. So let's go over another addition example, this time where we actually have to carry over. So we already know that 1010 is 10 in our decimal, but let's just add 1 to it, right? So we can go through the steps of converting it to 11, but we're adding 1 plus 10, we're just adding 1 to the binary. But let's go ahead and add it to our 101, okay? And of course we can lead it with a 0 as well. All right, so in this case, we're basically going to be adding the number 11 with the number 5, which we're going to try to get 16, and we'll see if that's going to work out in binary. Okay, so we're going to take binary 1 and binary 1, we're going to get them together, and of course we can't have the number 2. But what is the representation for 2? Well, that's a 1 and a 0. So we're going to bring down the 0 and we're going to carry over the 1. And then if you're going to have a 1 plus 1, again, you can't have a 2, so you're going to bring down the 0 and carry over a 1. And again, 1 plus 1, you're going to bring down the 0 and carry over 1. Well, this is going to be a good example because we carried the whole thing over, which is really cool. 1 plus 1 again is going to be 0, and we're going to carry over 1, right? And then we can add a leading 0 just so we don't lose place. And then we're going to bring down a 1. So of course this is the number 11. Oh, not 15. Woo, get rid of that. This is the number 11. This is the number 5. So in this is in base 10, and this is in base 10. So we're going to get the number 16 in base 10. Now, does this binary number represent 16 in base 10? Well, if we do our trick of 0 times 1 equals 0, 0 times 2 equals 0, 0 times 4 equals 0. And 0 times 8 equals 0. And 1 times 16 equals 0. Oops, not 0, 16. See, mathematical problems. You add them all up, you will get 16. So that's a good way of showing that we can still carry numbers over like we normally do. So now I would like to cover subtraction, because if you can add, you're going to probably want to subtract. So right now we're going to go over subtraction of binary numbers. And let's take, I think a good number would just be our 11, and then we're going to subtract it from our 5. Alright, so we know this is 11 in base 10, and this is 5 in base 10, and so the number that we're looking for here is going to be 6 in base 10. So we already know the answer, we're just seeing how we can manipulate the binary. Okay, so here we're going to take the top number, which is a binary 1, subtract it from a binary 1, and we're actually going to get a 0. Okay, if we take a 1 and we subtract 0 from it, we're actually going to get a 1. Now, can we take a 0 and subtract a 1 from it? No, we don't. And just like we did in our normal mathematics, if we had, let's say, a 10 minus 1, right? What do? We can't subtract 0 from this. So what we do is we cancel this out, and we bring the base 10 over for here, so then 10 minus 1 is 9. Okay? Well, the same thing that we're going to do, let's just make this clear, this is base 10 subtraction. Alright, so what we're going to do here is we can't take 1 away from 0, so what we're going to have to do is we're going to have to cancel this, and we're going to have to provide a base 2 number, right? This is 2, but really in binary 2 is a 1 0. Okay, so you can literally bring over the 1 0, but don't think that you can just take, oh, now this is a 9. No, don't get confused between that. It's really a binary representation of the number 2, and so you can now subtract 1 from 2, which is 1. Okay, and then if we were going to check our math, 0 times 1 equals 0. 1 times 2 equals 2. And 1 times 4 equals 4. And 4 plus 2 is 6. So as you can see, our subtraction works just the way it does in our addition, with the carryovers in addition and the subtraction or borrow froms in subtraction. All of the manipulations that you learned back in elementary school mathematics still apply to this numbering system, even though it's binary. Well, that's the basis of the binary numbering system and some common operations on the binary system. So I'd like to thank you for participating in this 10-minute networking workout. Once again, this is Jay Cooper Smith, and happy working out your networks.